Now, today's lesson is focused on the higher tier paper, so I do apologize to those of you who are doing foundation. However, I do think it's a really good idea if you do stay and just watch the lesson, because there's a lot to learn about graphs and about how graphs work in this today. So I think even if you're not doing higher tier, you can still pick up quite a lot of ideas about kind of how maths works and in theory behind graphs and equations and things. So yeah, there is a big focus today on the higher tier. We are continuing on with what we learned last time, so I hope you can remember the differentiation stuff that we did. I'll do a quick review at the beginning, and then we're going to be using differentiation. So we're going to be looking at what it actually means anyway and what it's all for, determining stationary points, okay, and what that means, and then distinguishing between the stationary points, so maximums and minimums. And hopefully, if we've got time at the end of the lesson, we'll be looking at some real world problem kind of problem solving ideas and just seeing what this all is useful for anyway. So I want to start by just doing a quick review of what we did last time. So kind of what is this all anyway? So last time we learned how to differentiate, and what's that all about? The best way to explain, well, differentiation is about rates of change. So it's about how looking at things change over time normally, but it doesn't have to be with time, but normally time. So in real life situations, the most kind of common thing that we look at, rate of change is on a distance time graph. Yeah, we're all used to the idea that if we divide distance by time, we get speed. Okay, so the gradient of the graph is the speed on a distance time graph. Okay, so imagine I'm walking along, and as time goes on, I'm walking, after 5 seconds, I've walked 10 meters. After 10 seconds, I've gone 20 meters and so on. So you can calculate my speed I'm walking from using this. You can say, well, okay, if I've walked 40 meters in 20 seconds, I'm walking at a pace of 2 meters per second. Okay, so I can work out my speed. And that's essentially what differentiation is. It's doing that. It's just finding rates of change of how things change. Okay. We don't use differentiation for problems like this. We just use division because we can, because this is a very simple concept of I divide 40 by 20, okay, and I find my speed. So we don't need differentiation for problems like this, but it's still the same concept. It's still that concept of finding the difference in one thing divided by the difference in another thing, okay? So there we go. The gradient of the graph there is speed. It's also known as the rate of change of distance over time, okay? That's another way of just saying what the speed is. So we could say that speed is distance over time, or we could say the speed is the difference in distance over the difference in time. And hopefully this kind of concept of d something by d something else, you've seen that, you saw that last week when we learned a little bit about differentiation, okay? So hopefully you'll see it really isn't any more complicated than just doing something like this. Let's have a look at a normal linear graph, so an algebraic graph now, okay? So this is a graph in the form y equals mx plus c. A few weeks ago, just checking. I just saw, hello, Faber, thank you for joining us. So a few weeks ago, we learned how to find the equation of this graph, or of a graph like this, okay? And we could do that right here. I can see instantly that my value of c is going to be -2 because it's there on the graph. So I can see that instantly. I can also work out, if I want to, I could work out, well, it goes along one and up one. Oh, no, it goes along one and I think up by 3/4. So I've got a feeling the gradient there is 3/4 or maybe 2/3. 2/3 actually, it goes along 3 there and up by 2, so it's 2 divided by 3. So the gradient of this is 2/3. So the point is that we can calculate the gradient on this graph and we can find the equation of this graph, okay? Gradient of the graph on there is just the steepness. But the gradient, what is it? It's just the rate of change of y over x. It's just how much y is changing over x. So we've found the gradient on this. Essentially, it's the same thing. It's kind of like differentiation, okay? It's just finding the difference in y over the difference in x. So the gradient is rise over run. We did that a few weeks ago, which is the same as the difference in y divided by the difference in x, or dy by dx there. And again, we don't need to use differentiation. We could use differentiation on this. If I wanted to, I could find the gradient of this by differentiating the equation, okay? I wouldn't normally do that because it's a lot quicker and easier just to find the gradient by doing our technique we learned, where we do a triangle, we go along, we find another, like 2 points, we draw the triangle on. Y there is 2, and x there is 3, so the gradient there is 2 over 3, okay? So my equation of this line is going to be y equals 2 over 3x minus 2. So that's a bit of revision there for you on straight line graphs. And now I can see, well, if I differentiate this, I would actually get that gradient. I'd get 2 over 3. So I wouldn't need to because I already know it, but I could use that technique there. So let's move on to our problem. What happens then if it's not a straight line, okay? So unfortunately, in real world situations, or probably fortunately, otherwise everything would be very boring, things always don't work quite as constant and lovely as we do put them in most mathematics problems. So, you know, we can give you a nice distance time graph and we can have a perfectly straight line and we can say calculate the speed, and you can calculate the speed. But most things don't work like that. You know, most joggers aren't jogging at a constant speed the whole time. Most cars aren't driving at constant speed the whole time. They have to slow down, they have to speed up, okay? So actually it's rarely going to be a perfect straight line that you're going to be calculating a gradient from in real life. So it's going to look something more like this, where it's kind of speeding up a little bit, accelerating here. It might go for constant, it might go at a constant speed for a while, and then it might need to slow down because, I don't know, it's a car and it's seen some traffic lights or something. So most distance time graphs would look something more like this, okay? And so we can't just calculate a nice simple gradient on here. We could calculate a nice simple gradient on this straight line bit by just dividing distance by time. But on these two bits, we can't just get, okay, my speed is a particular number, because there's no number for it. What's actually happening here is the speed is changing. Okay. Please do, if you've got any questions, please do ask. I'll keep an eye on the chat. My chat is up there on my screen, so I have to just remind myself. So put that up there as well. So the gradient of the graph is still the speed. Speed is still on this particular graph because it's distance divided by time, or distance and time. That's the graph. So its gradient is still telling us the speed, but the speed is not constant, okay? So we don't have a nice number. Instead, we can have an algebraic function. So if we know an equation of the graph, or if we can fit the graph to an equation, so I can say, well, this looks like a quadratic, part of a quadratic graph there, doesn't it? Because it's kind of got that curve. And this looks like part of a quadratic there. In fact, all of it together kind of looks like a cubic graph, doesn't it? Do you remember we looked at shapes of graphs? And so we could quite probably find an equation of a graph that would fit this. And we don't have to do that in GCSE maths. You don't have to actually find the equation that would fit that graph. But you do have to understand that that graph will fit some kind of equation, okay? So this graph will fit most likely a nice cubic equation or function there. And if we know that function, then we can use differentiation to find the gradient function of the graph. So we can differentiate the actual equation of the graph to find the gradient function of the graph. And it's called the gradient function, not just the gradient, because it's not going to be just a number. It's actually going to be a function. So you have to remember that a function is, and I've written this down somewhere, just something that happens to x. So let's have a look at this graph. Okay, so let's think what's happening on this graph. It's very simple. It's just y equals x squared. So on every x coordinate of this, we can find y coordinate by squaring it. Okay, that's this graph here. And we can look at all of these different points on this graph, and we can find the equation, we can find the gradient at all of these different points individually. I could come to this point here and I can say, well, at that exact point on the graph, I could draw like what's called a tangent to that graph, and I can find the gradient on there. Okay, done that really quickly. And I will just quickly show you again. I'm not going to do this for every single one, but on this particular gradient at this exact point there, I could draw that line, or I could draw in a triangle, sorry. I could find the difference in y, which is, it's hard to read off right now because I can find the difference in x there, and then I can find, divide one by the other and find the gradient there. And the gradient there is -6. I can come down here and I can do the same thing, but the gradient at this point is going to be different to the gradient at this point. See how the tangent at this point is steeper than the tangent at this point, okay? So the gradient at this point is going to be different. And again, down here, the gradient is going to be different. The graph is changing steepness all the way around. So at this point, it's -4. At this point here, we've got the gradient of 1. Okay, so that exact point, that tangent has a gradient of, sorry, -1. Thank goodness. There we go. Nope, -2 apparently. Let's have a look. So if I was to draw that and that, I would have had -2. Apologies. Okay. Here, that gradient is horizontal. The line at the tangent is horizontal. So that means that it's got 0 gradient. It doesn't have a gradient at all. So its gradient is 0. So all of these gradients were negative, and they were getting kind of less steep as the graph moved down towards the origin there. And then what happens on the other side? Well, the gradients are going to be getting more steep as the graph goes on up around there. So we've got +2, +4, and +6. Okay. So that's the number, that's the value of the gradient at each point on this graph. Does anyone want to have a guess at what the gradient function might be? Remember that the gradient function, okay, so we can find the gradient at any point on this graph by just doing something to the value of x. So let's have a look at here where x is 1, the gradient is 2. Here where x is 2, the gradient is 4. Here where x is 3, the gradient is 6. And then if we look at the other side where x is 1, gradient is -2. Where x is -2, the gradient is -4. Does anyone want to write in the chat for me what they think the gradient function might be? What might you have to do to x to get to the gradient on this one? Excellent. Thank you, Meadow. Well done. Correct. Yeah, it's x times 2. Okay, you just take the x value, you multiply it by 2, and you get the gradient. Okay. So I didn't write it down, did I? But yeah, the gradient there is 2x. Okay, I think I write it down on the next slide. So, okay, so how do we find the gradient of a curve? Well, if we had the curve of y equals x squared, that's what we just looked at. The gradient function there is 2x. And in general, for differentiation, we did this last week, or last lesson. If we have the function y equals a x to the power of n, the gradient function is y equals a times n. So you bring that down and you multiply it by a times x to the power of n minus 1. Okay. We talked last time a little bit about how this is a lot to remember. But if you can remember the pattern as opposed to the formula, it's easier. And the pattern is simply take the power, bring it down in front, and then subtract the power by 1. So we've taken that 2, we've put it in front, and we subtract the power by 1, okay? So if you can remember that pattern, it's easier to differentiate. So using that pattern, if we've got the curve of y equals x cubed, and that curve will look like something like this, okay, if you remember. Take the 3, put it down in front of the x, subtract the power by 1. Who's going to tell me? Oh, well done. I've got a correct answer from Tabitha as well there. Can someone put in the chat what the derivative, we call it the derivative, what dy by dx would be, the gradient function. Excellent. Well done, Tabitha. Really, really quick. 3x squared. Yes, well done. So take that 3, put it in front of the x, and subtract 1. It's really nice when people answer my questions. It means you're listening, which is really good, and following, which is really good. So thank you. And you got it correct. Well done. Okay. So we'll do a quick example and then we'll move on to using this and what it's all about anyway and all those things. So let's find the gradient. I've hidden a question there, but let's find the gradient function of the graph with equation y equals 4x cubed minus 6x squared minus x plus 3. And just to give you an idea of what this looks like, the graph looks like this, okay? So everywhere on this graph, if I take the x value, for example, if x is 1, I times it by 4, cube it, then times it by 4, then subtract 6 times 1 squared, and then subtract 1, and then add 3. If I do all of that to it, I will get the y coordinate, and I can plot that, and I could do that everywhere and get this graph, okay? So it just gives you a shape of the graph. So you'll notice that the gradient is changing all the way through. It's positive here. It's negative here. It's positive here. So it's changing all the way through. So it's going to be a function of x, and it's not going to be that easy because it's not going to be that nice and neat because of it being changing quite a lot. But it's actually not too hard to find the gradient because we just follow that rule. We take the power, we times it by the number in front, and we reduce the power by 1. And if we do that all the way through, we will get the gradient function. So let's do that. Oh, no, there we go. Okay, I'm going to do it writing. So dy by dx is going to be, take the power of 3, times it by the 4. So we've got 4 times 3, which is 12, x, reduce the power by 1, that becomes squared, minus, and then we do the same thing, bring the power down, multiply it by the number in front. So we've got 12 again, x, and then reducing that power by 1, we actually just get x to the power of 1, and x to the power of 1 is just x. So that's just 12x. And then here, remember that x to the power of 1 is just x, so I could treat this as x to the power of 1, okay? And then I can bring that 1 down and times it by this, which just is going to leave it as the same. So it's going to be minus 1. And then if I reduce 1 by 1, I get 0. Can anyone type in the chat for me? Oh, excellent. You got it all correct. Well done. Can anyone type in the chat for me? What is anything x to the power of 0? If I say it's 1, x to the power of 0, x to the power of 0 is going to be always very important for all students to know this. 1, excellent. Thank you very much. Correct, Tabitha. On the ball today. Meadow, well done. Good. So it's 1. Yeah, so that is just going to be 1. Okay. So it's just 1 times 1, which is 1. So that is the derivative or the gradient function of this graph here. And using that, I could now find the gradient anywhere on this graph, okay? So I could choose a point on this graph. I'm going to choose a really simple one. I'm going to choose 1, okay, because it's easy to substitute in. And I could see what the gradient is. Now, looking at the graph, I can see that it should be negative, okay? Because it's going in that direction, I think, just about, but not particularly steep. So if I was to do that at x equals 1, okay, let's have a look. Dy by dx is equal to 12 times 1 squared minus 12 times 1 minus 1. So it's actually going to be 12 times 1 squared is just 12 minus 12 minus 1. It's just minus 1. So it is negative, and it actually has a gradient of -1. So there we go. Okay, so that's a quite nice, easy point to check at. And you could do that anywhere. You could substitute the value of 2 in. Now 2 is going to be a really steep because it's obviously up there somewhere. So if I substituted 2 in, 12 times 2, that's going to be 12 times 2 squared is 4. So 12 times 4 is 48. Minus 12 is 36, minus 1 is 35. So it's got a gradient of 35, which is very, very steep. And it will be just up here somewhere. Okay, so you can see how quickly that gradient has changed on that graph, just between the values of x is 1 and x is 2. Okay, I've talked a lot. Does anyone have any questions at this point? Okay. Okay. So, do you want, oh, hang on. No, I didn't mean to do that. Here is the graph of y equals 4x cubed minus 6x squared minus x plus 3, which I think is the one we just differentiated. And it's got 3 changes in gradient, which I talked about just a little bit before. So you can see that at this point, the gradient is positive. At this point, the gradient is also positive. And at this point, the gradient is negative. So there we go. Okay. So questions in exams could ask you, and it's rare at GCSE really, A-level a little bit more they would, but they might ask you to point out like where on the graph the gradient is positive and where on the graph the gradient is negative, and it's really important you can do that. So you can look at the graph and you can see where that is, okay? But the more useful thing, and we'll go into this a little bit later after we've done the stationary points, the more useful thing is kind of recognizing where the gradient is changing, okay? So it's changing from here to here. It's going kind of through this point here, which is a maximum point, and changing from positive to negative. And then here it's changing from negative to positive. So those are the important parts of the graph. That's why generally when you look at algebraic graphs, we don't really worry about this bit. Kind of that's just going to keep going down and getting smaller and smaller and smaller forever now. And this bit's just going to keep getting greater and greater and greater, bigger and bigger forever now. It's this bit where it changes that we actually find useful things, actually can use that graph. So those are the important parts. And the same graph has 2 stationary points. So these turning points are the most important part of the graph. They're the most useful part. They're where actually it has 0 gradient, okay? So their gradient is 0 at that particular point there and at that particular point there, okay? So if this was a distance time graph, okay, if this was me, my distance changing, which would be on there, and my time over here, as time is going on, at this point, I'm actually moving towards, I don't know, home or something, okay? Let's imagine it's a speed time graph, actually. Let's imagine this is a speed time graph. So let's imagine that my speed is decreasing. And then at this moment here, I would actually have stopped, and then my speed would start increasing again, okay? So at this point here, you would see that there's 0 speed. So you can see that change in like how something is kind of happening. So that is the point there, okay? And those are really useful. They're also called turning points. So in your exam, you may see them called stationary points. You may see them called turning points. And you may be asked to find the coordinates of those turning points. And the fact that they have 0 gradient is your most important thing about that. So if you are asked to find the stationary points, let's have a look at this graph. I'm going to choose this graph as a quadratic. Quadratics are a little bit easier because they just have 1 stationary point, okay? So they've only got 1 turning point, and then that will just carry on going up there, and that will just carry on going up there, okay? So if they have no gradient, then the way we find the stationary point is we have to find the gradient function of the graph, which you know how to do, and then put it equal to 0, okay? Negative gradient, 0 gradient, positive gradient, there we go. So step 1 is going to be to find the gradient function of this graph. Does anyone want to type into the chat for me what the gradient function of this graph is? Have a go for me. It's really nice. Fabulous. Brilliant. Well done, Tabitha. Correct. Anyone else want to have? I think everyone's seen it now anyway. Hopefully that's what everyone else got to. So that's really, really good. Thank you. Yeah. And I think actually I've got it written up here. So yes, dy by dx is 2x plus 1. Okay, so that just tells us how we can find the gradient anywhere on here. Now it's this particular point I'm looking at. I'm looking for the coordinates of this stationary point on the graph. So at that point, I know that the gradient is equal to 0. Okay, it has no gradient at that point. So my step 2 will be to find the x coordinate, because it's x that's in the function there, by setting the gradient function equal to 0. So if I would set that equal to 0, I would have to find x by solving that equation. Does anyone want to solve that equation for me? Put it into the chat. Every single person should be able to do that. Foundation or higher. It was one of our first lessons. Oh, we've forgotten how to solve equations. That's okay. I'll do it quickly. Okay, it's been a while since we did any solving equations, so let's quickly go through it. So remember, when we solve equations, we literally just look for the inverse operation. So I'd be looking to subtract this one first on both sides. So if I subtract 1 from both sides, I'm going to have 2x equals -1. And then the second, oh, thank you very much. I've got a correct answer in the chat. Well done, Ava, thank you. The second inverse operation is to divide by 2. Perhaps I just didn't give you quite enough time. I'm sorry about that. And the answer is -1/2 or minus 0.5. So x coordinate is -0.5. Now, if you are given the graph in the exam to do when you're doing this, you can actually look over and you can just check, and that looks about right, doesn't it? Okay, there's 0. We're looking at the x coordinate, and so yeah, I'd say that's about sort of half a unit in here. Okay, so that's probably about right. So it's always good to just check. And so that's solving that equation. Okay, let's clear that, and we got, oh, there we go, 2x is -1/2 there. And step 3, sorry, I've just neatened that up a little bit and given you the answer before. Oops, sorry. Step 3 is to find the y coordinate. Okay, now at this point, I'm actually going to go back a step just because when you're doing step 3 and you're finding the y coordinates, this is where most people go wrong in the exam. And the reason why is because you cannot find the y coordinate from this, because this is actually telling us the gradient. It's not telling us the coordinates of the graph. The coordinates of the graph are given by this, the original graph, equation of the graph, okay? So if we want to find the y coordinate and we know the x coordinate, we have to go back to the original equation of the graph to find it. So finding the y coordinate is putting the x coordinate that we just found, which was x equals -1/2. X equals -1/2 there, okay, into that equation, which I'm just going to now go ahead and clear these and put that. So there we go. So the original function was y equals x squared plus x minus 2. Substituting x is -1/2. I've done that wrong there. I've put x as a half. Do make mistakes sometimes. I'm very sorry. So there we go. I need to change that to -1/2 there. Okay, and -1/2 there. And so actually that's going to be -1/2 squared, which is 1/4. Remember, negative numbers squared is positive because it's -1/2 times -1/2. Plus -1/2, which is the same as taking away a half, and then -2. Okay, so I'm going to use my calculator and cheat a little bit there. 1/4 minus 1/2 is -1/4, and then -2 is -9/4. So that answer should have been -9/4 there. Okay, so that's step 3, finding the y coordinate, is the bit where you just need to kind of remember to go back to your original function. So we'll have a look at doing some more of that. Does anyone have any questions about any of those things? I know I've kind of gone through quite a lot. Does anyone want me to go back through any of the steps, step 1, step 2, or step 3, before we move on? Pop it in the chat if you don't want to unmute yourself. We can do another, let's do this one more example here, okay? So let's just go through this example doing all of those steps and I'll just work it through with you, okay? So Find the coordinates of the turning point of the graph with this equation, 5x squared plus 2x minus 4. Okay, so step 1 was to, I'll do it in colours as well. Step 1 was to find dy by dx. If anyone wants to put dy by dx into the chat for me, please do have a go now. Remember, bring the power down, times by the number. Bring the power down, times by the number, reduce the power by 1. Everyone have a go at differentiating that for me. Fabulous. One correct answer. Well done. Anyone else going to put it in? Another minute. Nope. Okay. Oh, yeah, excellent. Another correct answer. Good. Well done. So, yes, so we're going to bring the power down. So times it by 5. 2 times 5 is 10. X, and then reducing that power by 1 is just power of 1. Plus, and then here we are literally bringing the power down 1, and then it disappears because the x becomes x to the power of 0, and then the constant term disappears completely. So I'm really impressed that some of you are getting that right, because we did that last time, and I've just done it super quickly today, and I've explained it really quickly, but last lesson does kind of go into this a lot more detail. So if you have forgotten, you can have a look on last lesson, the recording from that. Step 2, we need to find the turning point, and the turning point is this bit here, this exact point where its gradient is 0, okay? So we set the gradient to 0, 10x plus 2 equals 0. In exams, you literally get a whole mark just for writing the equals 0 bit, because it shows that you understand that the gradient is 0 at the turning point. So it's a really nice little free mark that you get just for writing that equals 0 bit there, okay? Then you have to solve it. Okay, so subtracting that 2 first. Anyone wants to get the answer into the chat before I can get it written on here? Please do. Okay, next part is going to be to divide by 10. And so x is going to be equal to minus 2 divided by 10. And then I'm going to use my equivalent fractions. That's minus 1 divided by 5. And I can write that as a decimal, as Meadow has already, and Tabitha has already got correct. Well done. Minus 0.2. So fabulous. Okay. Thank you. I'm going to have to tidy up a bit though, because I haven't got enough space now to write all of that. So there we go. I wonder if I can just move that up there. There we go. Okay. And then step 3. Can anyone remember what step 3 was to do? Or how do I do it? I need to find the y coordinate, because I found the x coordinate is at minus 0.2. Do I find the y coordinate by substituting into here or into here? Excellent. Well done. Put x back into the equation. Good. So putting x back into the equation for y, that's a good hint, because we're looking for the y coordinate. So we need y, okay, is going to be 5 times minus 0.2 squared plus 2 times minus 0.2, and then minus 4, which is going to be 5 times 0.04, I believe, plus minus 0.4 minus 4. And that is going to be 0.2 minus 0.4, which is minus 0.2, 3.8, I think. No, that can't be right, can it? Let's have a look. Do put the answer in the equation if you get there faster than me. Minus 4.2. I think I added, there we go, minus 4.2. So I added it on rather than taking it away. I was going to say it has to be negative because look, it's down here below minus 4. Okay, so the answer then, the coordinates, my final answer in the step 4 should probably be to write the final answer as a coordinate, okay? Final answer is going to be x is minus 0.2. Oh, and y is minus 4.2 there, okay? So that is the coordinates of that stationary, or that turning point, stationary point there for you. Okay. How are people feeling about, if you've got your camera on, give me a thumbs up or a not so happy about today. It's probably one of the more complicated topics in the higher tier. So if you're feeling good about it, then that's really good because it is, wow, I mean, a lot of exam boards don't do this at GCSE. A lot of exam boards only do it at A level. So the fact that you're doing it in the EdExcel course, the international, the IAL course, it's really good. But it's definitely more challenging. Okay, let's move on. If you're feeling good, I see a thumbs up in the chat. So I was about to say, if you're feeling confident, we can have a look at doing the turning points of the graph of equation y equals 2x cubed plus 3.5 x squared minus 3x plus 5. Now, this has got 2 turning points. So this means we need to find 2 sets of coordinates, okay? 2 coordinates. We need to find one here and one here. So we can have a look at doing this. This is definitely probably as challenging as this topic gets. So don't stress too much. I will definitely go through it with you. Oh, whoops. So step 1 is going to be to differentiate this. So once again, if you want to differentiate it and pop your answer in the chat, do have a go. I'm going to go through this here. So differentiating is going to be bringing that 3 down and timesing by 2. We've got 6x plus. Being confident with this method is great for the GCSE because you do get 1 mark for every single term you differentiate. So there's quite a lot of marks in it in the exam, okay? So 6x, I forgot the squared there, didn't I? 2 times 3x, reduce the power by 1, and then bring the 2 down and times it by 3.5 and reduce the power by 1, so that's x. And then here, minus 3. Fabulous. You got there quicker than me, Tabitha. I'm really impressed, okay? So that was step 1. Step 2 is going to be setting the equation equal to 0. And you'll see that because we've got a quadratic, so 6x squared plus 7x minus 3, setting that equal to 0, okay, gives us 2 answers, 2 possible answers for this, okay? Now, solving quadratics, we did a long time ago. Can you remember how to solve quadratics? Who can remember how to solve quadratics? There's 3 different methods. There is factorizing, using the quadratic formula, or completing the square. Which one do you think you should do for this particular question to solve this quadratic? Would you go for factorizing? You may well be able to factorize this, or would you go for quadratic formula or completing the square? If you don't know, don't worry. If you do know, or if you just want to have a guess, pop an answer in the chat. If you were sat in an exam, how would you solve this? So Meadow's saying factorizing. Now, I do think that this can be factorized, in fact. 18, I'm just trying to think now. 7. It probably can be factorized. I would go with the quadratic formula. Now, the only reason why I would is because factorizing for me, because of this 6, would take a while. So it most likely can be factorized. And let me have a look. Yes, it can be factorized. Okay, so if we do factorize it, we are going to get a 3x and a 2x there, and then we would need to think what's going to be there. So what is going to be there? That's going to be plus 3, and that's going to be minus 1 equals 0. And I think, did I teach you the treat way to factorize when we did solving quadratics a long time ago? Where you just type it into your equation, get the answers, and then put it back into the brackets. I may have taught you that. That's what I just did, basically. So it's much easier to do that. Otherwise, you kind of have to go, what two numbers multiply together to get 6 or to get 18? What two numbers are going to go there? So otherwise, it's kind of a big play of trial and error to get to these values. Okay, so factorizing is possible. I think that factorizing is probably a little bit tricky with this, just because that 6, there's so many options. This could be a 3 and a 2, or it could be a 2 and a 3, it could be a 6 and a 1. This could then be like, there's a lot of options and it might take a while. So that is one method. I would probably do this in an exam I would most likely do it using my calculator. If you've got this kind of calculator, I'll just put that into the video. If you've got this kind of calculator, you can solve a quadratic on it. I would definitely recommend you do that. Most calculators do. It's only kind of the older calculators that don't solve a quadratic. But I do highly recommend when you go into your exam, you have one that can solve a quadratic, because doing a problem like this and getting that answer quite quickly is going to save you a lot of time, rather than having to put it all into the quadratic formula. But if you are doing the quadratic formula, then you just have to remember it's minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. So you substitute all those values in, and you remember that. So that's another method for solving quadratics. We've kind of gone off on a tangent now. We were learning about differentiation. So I'm going to just do this really quickly. Minus 7 plus or minus the square root of 7 squared minus 4 times 6 times minus 3, all divided by 2 times 6. Type that all in your calculator and get the answer, and the answers you will get will be, because you've got a plus and a minus, you'll get two answers. X equals minus 3 over 2, or X equals 1 over 3. Okay. There was a lesson a long time ago on quadratic equations and solving them. So you can go back and review that if you need some extra work on solving quadratics. Okay. Ooh. I was just trying to move that up a little bit. There we go. So in a question like this, most often you can just type it into your calculator and get your calculator to solve it for you. Do that trick of like reverse factorizing to show some working there if you have time. But if you don't have time, just do that. Okay. So that was step 2. Sorry, that took a long time. So step 1 was to differentiate. Step 2 was to solve the equation. Step 3 is to do what? Oh, you did put it in the thing earlier, to find the y coordinates by substituting it back in. So y is equal to, and then again, you really are heavily reliant on your calculator here, because I would not try and do this. You wouldn't get a question like this in a non-calculator paper anyway. I would not try and do this without your calculator here. So type that all into your calculator and get the answer there. So you would get one turning point there. I'm going to call it Y1 just for ease, because it's easier sometimes just to differentiate them, to find the difference between them by just saying that this is X1 and I put X1 into Y1, and this is X2 and I put X2 into Y2 there. So we've got 2 times 1 over 3 cubed plus 3.5 times 1 over 3 squared minus 3 times 1 over 3 plus 5 And typing all of that into your calculator gives you that second coordinate there. So if anyone wants to find if anyone's got the calculator handy and wants to find what those are, please do pop them in the chat for me. And the last thing I want to do with you is I want to talk about, once we know what these y coordinates are, I want to talk about how we would know which one is which, okay? So knowing which one is which is simply looking at the value of x. So we've got x1 here is minus 3 over 2. So that means that x1 must be this one here. This one is minus 3 over 2 because that's where x is negative. And this one here is where x is positive, so that must be 1 over 3. So that's kind of the last thing you need to do is make sure you don't get the coordinates the wrong way around, okay? This one is positive x, this one is negative x, okay? So just assigning them to the correct one there. And I'm not too worried about finding the actual y values. Can do it. You would obviously definitely do it in the exam if that was part of the question. I just think for now. Cubed plus 5, I thought. Minus. Has anyone done them? No. It's a while. Okay, so for that first one, I got 13 over 8 or 1.625. I'm going to leave it as a fraction there, okay? I'm not going to do the second one right now, but hopefully you're confident with substituting those values in and typing them into your calculator. Just type them in exactly as you see them, okay? If you've got a calculator like this, it's really easy. You just use the arrow keys and the fraction key. Type it in exactly as you can, as you see it, okay? So, we've talked about stationary points, okay? So stationary points, like I did mention earlier, they are either minimum points, and minimum points are obviously the points where it turns at the bottom there, because that's the kind of smallest value that the graph gets to, or they're maximum points there, okay? That's the greatest value that the graph gets to. So on a cubic graph, we call them the local maximum and the local minimum. And that is because actually this is a maximum point, but it's not the greatest point that the whole graph gets to, because you can see that the graph here continues on getting bigger there. And then this is a local minimum because it's not the smallest point that the graph gets to. It actually can go smaller there, but it's at that kind of local point there. That's the smallest point, and then it goes down and it continues going up afterwards. So you will see those words, okay? And you might be asked to find the maximum point or the minimum point or the maximum value and a minimum value, okay? So you may be asked to determine whether a point is a maximum or minimum. And if you are, it's normally really obvious, okay? Not sometimes, normally. Because for example, if you know the graph is a positive quadratic, and positive quadratics are where the number in front of the x squared is positive, then the graph has to be, I think I called it a smile graph last time, didn't I? Okay, if it looks like that, then it can only possibly be a minimum, okay? And then if it's a negative quadratic, so if it was, for example, y equals minus 5x squared plus blah, 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 then it could only possibly be a maximum point, because the graph there it has to go that way. So if you know the shape of the graph, or if you're kind of familiar with what graphs look like, which you will be, because you have to be when you go into your exam, then it's just really easy. You just think, okay, well, this is a positive quadratic, so it's got to be a minimum point. This is a negative quadratic, so it's got to be a maximum point. Okay, for other graphs, you might actually have to think about it, but that's okay. So for this one, there's a cubic, okay? And again, it's looking at whether it's positive or negative. This is a positive cubic graph. And a positive cubic graph, we talked about those last time. They're the ones that go in the positive direction. So they're kind of going like that. So that means that the maximum comes before the minimum. So the maximum point will be the lower value of x, the smaller value of x. Might not always be that the maximum is negative x and the minimum is positive. It might be that it's like that, where they're both in the positive, x is positive in there and there, but you can see that the maximum is still before the minimum. So the maximum is just a smaller value of x, okay? And then if you had a negative cubic, and a negative cubic just would be like y equals minus 2x cubed plus and all the rest of it. Negative cubics are the ones where the graph goes the other way. So the graph goes like that. I don't know why I'm finding that hard to draw. Yeah, that's right. No, hang on. Like that. There we go. So in that graph, the minimum comes before the maximum. Okay, so they will look like that. And so you can think about the shape of the graph, and then you can look at where the coordinates or where those turning points will be. Any questions? Giving you a lot of information again today. These lessons are always lots of information. Oh, there we go. This is a better graph, isn't it? If the graph is a positive cubic, then the first turning point is A. That's wrong. That should be a maximum. There's a maximum point because you can see there positive cubic is the maximum before minimum. Local maximum is the smaller x coordinate. Local minimum is the bigger x coordinate. So I should have said maximum there. Apologies to change this. And this is the wrong way around as well. If the graph is a negative cubic, that's a picture of a negative cubic graph, then the turning point, well, the first turning point, this turning point is a minimum here, and then the next turning point is a maximum there, okay? So this is your local minimum, followed by your local maximum. So the smaller x coordinate is the minimum and the bigger x coordinate is the maximum. That's a better graph for you to look at. Okay. And I don't know if we have time to do this. I will have a quick go at doing this. I wanted to just put kind of one example of problem solving in. So why is this useful? I want to just quickly do this example so you can see. So I want to, you imagine you're given a part of the garden to use as your vegetable growing plot. Will you ever have to draw? Yeah, you might have to draw a cubic graph in the exam. Good question. And if you do have to draw a cubic graph, then you will most likely be given like a table of values. So you'll be given either y equals, I don't know, like 3x cubed plus 2x. Sorry, everyone, just for everyone, if anyone didn't spot, Meadow just asked the question if you have to draw a cubic graph in the exam. So I'm just answering that question quickly before I continue on with this. So yeah, you might be given a kind of cubic graph like that, and you'll be given a table with some x and y values, and then all of the x values will be given, and some of the y values will be given, and you would find the rest of the y values. You'd also be given the axes and everything, and you'd plot those coordinates and draw the graph. Usually it's a quadratic, but it could be a cubic. There is a possibility that it could be a cubic. So you should know what the shape is to kind of know what to expect. Okay. Right. So let's do this quickly. So you've been given some kind of rules. You've been given 5 meters of fence, okay, to separate your plot. So you're going to build your plot with 5 meters of fence. And the 2 conditions are that your plot must fit against the back wall of the garden. So I'm going to draw this kind of back wall here. This is my wall. All right. And you must keep your plot in the shape of a rectangle. Okay, you're welcome. So your plot is going to be a rectangle like this. It has to be a rectangle. Otherwise, my question won't work. So it will be, those 2 will be the same. So if you were going to do a question like this, and this is probably a little bit beyond GCSE. I don't think they would ask this in GCSE. This is more just kind of just to give you an idea of like how this works. They do say that they could ask these kind of questions, but I honestly have never seen a question like this asked. And if they did, they would definitely guide you through how to do it. But to do this, we don't know the size of this rectangle. All we know is that this plus this plus this is the fence. So they have to add up to 5. So if we're going to make these add up to 5, and we want to make the biggest possible area using these 5 meters, okay? So what I'm going to do is I'm going to say, well, these two are the same. So if I call these X, and I know that this plus this have to equal 5, this is going to be different. These are the same, so that's X and that's X, but this is going to be Y. So I'm going to say that I know that X plus Y plus X plus Y plus X have to be equal to 5, okay? And so I can simplify that. So simplifying that, we would have 2X plus Y are equal to 5. So my fence in total has to be 5 meters. Now the length of the fence is no good to me as Y, okay? Because it's different and I want it to be equal. I want X all the way through. But I can actually rewrite Y in terms of X. What would it be if I was to make Y the subject of this equation? Think back to making Y the subject of an equation. I'm sorry, we are going to go a little bit over because we've only got 2 minutes. Can anyone pop in the chat for me? Do feel free to go if you need to. Otherwise, pop in the chat. What would it be? Excellent. Well done. 5 minus 2x. Thank you very much. So instead of having y here, I'm going to rewrite that as 5 minus 2x. Okay. Now that I have my rectangle and the lengths of my rectangle are both in terms of x, okay, and I know that if I add them up, I'm going to get them to be equal to 5 because x plus 5 minus 2x is 5. Okay, so that's all good. I can write down an expression for the area of my garden. What would the area of my garden be? How would I find the area of that rectangle? Pop it in the chat if you can. It's going to be an expression in terms of x for the area of the rectangle. Remember, the area of a rectangle is length times width. I'm going to just go ahead and write it down. So the area of a rectangle is length times width. So it's excellent. Thank you. So it's 5 times, 5 minus 2x times x. I'm going to times the length by the width. When we do times an expression by a value like that, we do remember to put brackets, don't we? So if x times 5 minus 2x, and then I am going to multiply that out, and I'm going to say 5x minus 2x squared is my area. So now I have an expression for the area. I'm going to change it just to be a equals minus 2x squared plus 5x. And what you'll notice is that my expression for an area is a negative quadratic, isn't it? Okay, because the highest power of x is x squared, and it's got negative in front of the x squared. So if I was to draw a graph for my area, okay, then my graph would look something like this. It wouldn't look like that because I wouldn't have negative values of x, would I? So I'm going to put it all like that. Okay, I don't know exactly what my graph looks like. I haven't worked out exactly what the coordinates are, but I do know that the shape of it is like this. In fact, I don't even need to put axes on there because I don't know where it sits on the axes. What I do know is that it has a local maximum, or it has a maximum point. Okay, there is a point on this graph that x can be at that will create my area to be at a maximum. Remember, this is how x changes, and this is how a changes. Okay, so if I did have axes, I'll put them back on now. This would be the x-axis. This is the kind of value of the width. And this is the A. This is how the area changes as the x changes. And at some point, that area is maximized, and I want to find the value of x that allows me to have the biggest area. And to do that, I differentiate. I find dA by dx. Okay? So differentiating dA by dx, I'm finding the gradient is going to be, bring that power down. So minus 4x plus 5, okay? So differentiating that, I know that my gradient function is minus 4x plus 5. So all along here, I can find the gradient on that graph by just timesing it by minus 4 and adding 5, okay? Now, I want to find where that maximum, where the gradient is, where the gradient is equal to 0. Where the maximum point is where the gradient is equal to 0. So to find that maximum point, I'm going to let that gradient be equal to 0. So I'm going to say that is equal to 0. And then I solve it. So minus 4x is equal to minus 5. And x then is equal to 5 divided by 4, which is 1.25. So x is equal to 1.25. Okay, so I'm sorry I've done that quite quickly, but hopefully you've managed to kind of follow the concept of why differentiation is quite useful, because I know now that if I make x 1.25 meters, I can create the biggest possible area with 5 meters of fence in this situation, okay? So that's just a kind of an idea of applying differentiation to real life. And I'm very, very sorry that we have gone over. So I will stop right there and let you all go and enjoy your evenings.